So with this background, a very good afternoon to all of you, the speakers, the presenters, as well as all the participants who have joined from various parts of the country. On behalf of the Alliance for an Energy Efficient Economy, popularly known as AEEE, it is my pleasure to welcome the presenter and attendees to this webinar on optimized load estimation and low-emission HVAC solutions. My name is Ritobroto Sen. I work as a Senior Manager Industry Engagement at AEEE, and I'm joined by my colleagues Pramod Kumar Singh, Senior Director, Research and Programs. He has joined online. To my right, to my opposite, it is Ranavir Pratap Singh. He is a Principal Research Associate at AEEE. And to my right, we have Bhairav Sharma, who is a Manager, Membership and Training at AEEE. So for the sake of saving time, I have taken the liberty to introduce them at a very with their names and designations, and I'm sure they will be speaking in due course in this webinar. A very brief introduction in a couple of slides. In a couple of slides about AEEE. So this slide that you see on your screen, I hope the slide has changed, Pramod. If you could please confirm. Okay, so the slide that you see on your screen, it gives summarizes what AEEE is. I will not read out from the slide, but in addition to what you see on your screen, just to give you an overview of the organization, so AEEE promotes energy efficiency as a resource and collaborates with industry and government to transform the market for energy efficient products and services, thereby contributing toward meeting India's goals on energy security, clean energy, and climate change. But probably one of the unique distinguishing characteristics of AEEE is that we are a premier industry-led research organization. So you might find many research organizations, think tanks, but we focus on applied research, and second, which benefits the industry. And second is our strength is our member-driven organization. The board and the membership base that we have typically comes from the industry and in the sectors, especially that we work with. As of today, as you can see at the number at the bottom left, we have 78 member organizations, and many of them are involved directly or indirectly in our research projects. So we want to have only those members in our domain, in our ecosystem, whom we can add value, and vice versa through our research projects. Just one more slide about our focus areas, the work areas that AEEE operates in. So typically our one of the major verticals that we operate in is the low carbon built environment, followed by sustainable cooling, cold chain, smart and resilient power, and smart mobility, especially on the demand side is where we focus on the smart and resilient power. Of course, there are bullet points highlighting the focus areas under each of these vertical. Then we also work, as I said, very closely with the government. That is what covers under the global and local action. That is our work with various central government agencies as well as state level agencies as well. In few cases, we have worked with, especially when India was the G20 president, we have worked at an international scale as well. And finally, the last vertical known as decarbonization catalysts, which are certain areas, as you can see, ESCOs, capacity building, financing. So these are cross-cutting. So this particular vertical supports the other four verticals. So it is like a cross-cutting vertical across the other four. So if you follow us on our social media and do visit our website, you will get access to a lot of our research reports and know about various other initiatives that we do. Finally, a couple of points or a couple of lines about the ION Zero webinar series. So as you have joined today is the third episode under the ION Zero AEEE webinar series. The way it was curated was that we will offer deep dive into critical solutions to achieve net zero, and that is why it is ION Zero. The episodes under this series cover 4 thematic areas: latest product and technology innovations, that is what we are focusing on today. And the other 3 thematic areas are breakthrough financing models, evolving regulatory policies, and emerging career and skilling opportunities in the net zero ecosystem. Presentations today, that is in the third episode under this series, will be delivered by industry experts from 2 leading AEEE member organizations. And I would request Prashantji first to take about 30 seconds to a minute to introduce himself briefly. We are not reading out your bio. We will request you to introduce yourself, followed by Mr. Apurva Bose from Triveni Turbines. So Prashantji, if you could unmute yourself and please introduce yourself.
Sure. Thank you. Thanks for setting that context about AEEE. Well, I am with Carrier for last 18 plus years, and overall experience is about 25 years in the industry. And I lead the initiative known as Commercial Applied Solutions, which does not only talk about product, but also about solutions around HVAC, products as well as market initiatives. That's it from my side. We can deliberate more on that later.
Mr. Bose.
Hi, good afternoon, everyone. My name is Apurv, and I'm working with Triveni Turbines since last 3 and a half years. So I have joined here because Triveni wanted to initiate a new vertical with a new technology products. So that's what I'm leading, and these are all green products, which we will talk more about going forward. More than that, I'm predominantly having more than 3 decades of industry experience, predominantly into turbo machinery, refrigeration, and also automotive. So these are something which I just want to talk about myself. Thank you.
Thank you, Mr. Dixit. Thank you, Mr. Bose. So with this brief background, I would now request my colleague Pramod to please set the context for today's webinar. Pramod, over to you.
Thanks, Ritabhrata. Good afternoon, everyone, and once again, a very warm AEEE welcome to all the participants and the speakers. It's a great honor to address on a topic that is so critical for our future. Viksit Bharat 2047 is India's vision to transform into a developed country. And to achieve this vision, we know energy is going to play a crucial role. Our energy demand by 2047 is expected to grow approximately 2 to 2.5 times in the next 20 years. They say no amount of water is sufficient to fill a bucket that is already leaking. So as we move forward, let us remember that the most sustainable energy is the energy use that can be avoided through efficiency. Consider the fact that minus energy efficiency, India's energy consumption in the previous year would have been 9% higher. Our carbon emissions would have been 10% higher. That's the contribution energy efficiency has made to our economy, which means efficiency is not just a side strategy or a good to do thing. Let's do energy conservation. It's the nice thing to do. It's a crucial pillar of our clean energy transition. Without efficiency, our energy imports is going to be significantly higher. The investment required in energy supply infrastructure, that's also going to be very high. Overall, impacting the competitiveness of our economy. But when we save energy, we save money, we save the country, we save the planet. There is a misconception that efficiency often or always results in operational savings. It's a OPEX reduction measure. But at AEEE, we say that's a myth. Energy efficiency can also lead to CAPEX savings. How? At AEEE, we promote the concept of lean, mean, green, and seen. And I will explain this in the context of cooling. So whenever we design a building, how do we properly plan for the envelope, the outer shell of the building, so that the cooling requirement first can be reduced, and right sizing of cooling equipments can be planned. That's the lean philosophy. Under the mean philosophy, we say careful selection of equipments which are energy efficient so that the customers enjoy operational cost savings, And then you plan for putting rooftop solar, renewable, planning for renewable purchase. That's the green approach. And finally, whatever a customer is doing, it's very important to, to monitor the savings, to document the savings so that it's visible to everyone in a very transparent way. So that's the lean, mean, green approach. If the solutions are carefully selected, carefully sized, combined, and sequenced, then it's not only about operational savings, energy efficiency can lead to capex savings as well. Which brings us to today's topic also. I'm sure everyone is aware about the cooling scenario in India and the future requirements. Let me share 2-3 key statistics. When it comes to room air conditioners, in 2024, India sold 14 million room air conditioners, approximately 20 million TR. When it comes to commercial AC, last year the sales was approximately 2.5 to 3 million TR. Building sector contribute 30% to India's electricity consumption. And within the building sector, the share of air conditioning is almost 40 to 60%. That's the government estimates. If we talk about contribution of AC in national peak demand, ACs contribute almost 20%, 50 to 60 gigawatt. And this number is expected to grow manyfold in the next 20 years. So in today's webinar, we are going to hear on two important aspects: how to reduce the energy consumption and environmental impact of HVAC system. The problem which we are trying to address, what is hurting the industry is rule of thumb and safety margin. Optimized load estimation tools can help to right size the system and avoid these thumb rules and safety margin factors which lead to oversizing. Similarly, on the refrigerant front, India has a commitment to go for HFC phase down by 2047. And there is a need to transition towards natural refrigerants such as CO2 based systems, ammonia based systems. And they will offer a dual benefit of reducing the emissions from HVAC sector as well as to meet India's commitment. We'll also hear about the simultaneous use of cooling and heating technologies that can deliver very high level of efficiency. So once again, I welcome these two speakers, Mr. Dikshit and Mr. Bose, and who are going to share practical insights on sizing of our efficient system as well as use of natural refrigerant based innovative solutions. I would like to conclude by saying today, if we are not part of the solution, then we are part of the pollution. So let's work together to address the greatest challenge of climate change that all of us are facing. And thank you, and I wish everyone a very productive and insightful session. Over to you, Ritu.
Thank you, Pramod. That sets it up perfectly. So just a couple of hygiene points for our attendees. We'll try to be as interactive in the sense we'll try to take up all your questions, as I said. So please put your questions in the Q&A box. And if you are facing any issues in terms of volume or audio, video, any of such issues, please put it in the chat box. But otherwise, purely questions addressed to the speakers, try to put it in the Q&A box, please. So with this, I would invite the first speaker, Mr. Prashant Dikshit from Carrier, to please share the screen and begin his presentation. Prashantji, as you know, you will have 25 minutes, and we will want to stick to that. And if required, I'll give you a ping at the 20th minute so that you are aware that you have to wrap it in the next 5 minutes after that. Over to you, Prashantji.
Sure. Thank you. I think Mr. Pramod has set the context, which has helped me, rather, rushing through the hygiene slides. Okay. So very good afternoon to everyone. In the interest of video and audio clarity, I'll put myself also on the, non-video mode rather, or maybe I can go ahead. All right. So we're all aware, that what is the global energy emission contribution, which is coming from the energy sector? It's a staggering number, which stands at close to about 73%. And from that, energy, look at this number, which is close to 40% is coming from buildings. I'm talking about global energy emissions and buildings contributing nearly 40%. And if I go to the further breakdown, nearly 11% is coming from HVAC. And of course, 4% is coming from cold chain. And in the cold chain, of course, I'm not addressing something which is from the food waste, just purely the cold chain which is responsible. When we make the equation and try figure out what is our contribution from the HVAC side, it's 15%. This is not a number to ignore. So we have action pending at our end. While a lot of this is being addressed, but a long way to go. Well, how does it connect the dots? Out of that 40%, now HVAC in a building is going to consume about 50%. This is an average number. Some buildings, most efficient buildings, may be consuming 40%, but some also probably go to 60, depending upon the climatic zones they are, the design philosophies they have adopted. But let's take a number to start with as 50%. Now, I'm sure all of you are aware about SBTI. And for the people who are new to this, SBTI is nothing but a science-based target initiative. You can't just go around and tell that I'll be carbon neutral, I'll reduce carbon and all that. It asks for the initiatives. What is that you are trying to do to achieve so and so commitments? By when? It's a very philosophical, scientifically proven, methodological, and it gives us a clear guideline ki if at all I have to reach something called as net zero, where should I start? How should I achieve? What are the measures? What are levers at my hand? So you can probably read up on the website about SBTI. This is something which basically governs the net zero roadmap for us as corporates and end users. Now, we all know that there are three different buckets when it comes to these aspects. We call them in three different names: scope 1, scope 2, scope 3. The scope 1, scope 2, scope 3 can vary where you stand. All right. So one which is clearly a direct emission, which means I am doing something at my premises and I'm releasing greenhouse gases to the atmosphere. It could be a manufacturing plant. It could be anything for that matter where I'm doing some exhaust, and it is called as direct. Then comes indirect. What does indirect means? Here, I am purchasing the energy. All right. But to produce that energy, somebody else is probably burning the coal. Right. Indirectly, I am contributing for CO2 emissions. And then the third comes is that no matter where you stand, you are bound to go through this cycle, which means there is a raw material which is required. There is a supplier who manufactures or provides you the raw material, and then manufacturing happens, then the distribution happens, then it goes to the customer and then the consumer. You think of this cycle, you can be anywhere, but you are definitely part of this cycle. So many people focus on direct emission. Some people have started to focus around indirect emission, but the bigger value is in the value chain emission, which probably is scope 3 when I start talking from my perspective. So what are the ways and means we have currently available with us? What can I do? The first and foremost and easy access available to all of us was carbon offsets. Hey, look, I have money. You tell me, I'll purchase those carbon credits and offset my carbon, emissions. Well, I mean, is this this is okay to start with, but is this sustainable? You can neutralize only close to about 5 to 10% of your emissions, but beyond that, no. Then yes, the immediate alternative solution which is available with us is renewable energy. I'm happy to share that this sector is gaining a lot of momentum traction and is definitely contributing in reduction of coal-based energies. It's a very good thing, but look at the limitations. How many buildings will be able to employ solar? How many buildings we will be able to install a windmill? Or do we have the feasibility at every place considering our weather conditions, our portfolio of the buildings? So then maybe another 10 to 15%, or in some cases, maybe we go to close to about 50% also. But the bucket which we intend to target is about energy efficiency. This is in our hands. This is in our hands by selecting or choosing a right system. When I say the choosing a right system means you put your mind, you put your design philosophy with mind that I'm going to achieve the net zero, not just by embodied carbon, but also by operational carbon. I'll touch upon this as we move forward, but let me tell you, this is the area where we as an engineers can contribute greatly. How can we improvise on this? So that's why I called it as 3 major pathways to achieve net zero goals. Well, we all talk about HVAC, and any HVAC system, if we take today, is at least about 12 to 15 years when we use a air cooled kind of a system, and it goes as high as 20 years when we talk about, say, water cooled systems. So each and every solution involves 3 critical components, starting with design and then enabling the user and delivering on the commitment with respect to our net zero goals. So this is a slide where I would like to explain in the energy efficient product and solution, what all HVAC can come up with. One, definitely you can come up with a very highly efficient product. There are heat pump solutions available. My next speaker is going to probably talk about that. We have concepts around evaporative cooling wherever your environment supports you. In a larger plant like big pharmas or data centers, or I would call as district cooling systems, you can think of series counter flow designs. On top of it, you can also put a BMS system, or we call it as chiller plant manager systems, to top it up, which means you have pretty much everything covered under energy efficiency in terms of products and solution. But what more? During the next cycle, which is aftermarket, the 4-5 checkpoints, a health check of an equipment, predictive insight. We are living in the age of AI and IoTs today. It is not difficult to predict failures. It's not difficult to predict something which is going off the track. Cooling as a service. This is catching up. We will definitely address this as one of a topic in some other sessions in AEEE, but it's a wonderful concept to talk about. We're talking about remote monitoring and diagnostics, which, by the way, can save a lot of time and energy. Think of a situation when there is a call breakdown and you register a call to a call center, and that call center will assign the call to somebody, and that somebody is not always at your site. He's somewhere and he has to go all the way to your site. Think of the carbon emissions which he is doing directly, but at the same time, once he reaches there, he may have to process through the security gate, multiple things, right? If at all you give your equipment on a remote monitoring, all this can be avoided. Yes, only absolute necessity, you go probably and attend to that fault. Then advisory services. Assume that in case if there is a benchmark set, and if that benchmark is not being achieved, you can look into that. That's the next layer. When it comes to the third layer, which is energy and carbon audit with guaranteed performance, earlier days, the emphasis has been mostly around chiller efficiency or at best plant room efficiency. But unfortunately, the trend with guaranteed performance is still lacking in the market. Tenders, many consultants want this to be part of it, but unfortunately, the system is not yet prepared to commit on that. However, we through this channel would like to advocate that we have to reach there to ensure that we work together as a HVAC organization, just not as a chiller manufacturer or a pump manufacturer, come together to ensure that plant level efficiencies are adhered to whatever is committed. And of course, in a brownfield project, you can look into retrofits, you can look into the installation of controls and things like that. Over and above that, to do anything, you need data, and that data needs to be visualized properly. So there are a lot of markets which is emerging with respect to digitization and subscription model, right? So today we are not only talking about efficient building, we are also talking about healthy building because of the emphasis on indoor air qualities, especially post COVID era. We have all learned it hard way that how important the indoor air, quality is all about. Well, there can be products and solutions, there can be service and modernizations, there can be digital driven operations possibilities, which ensures that, there is a minimal OPEX, End of the day, money matters. Uptime, ESG goals are met. I'm not going to address about ESG goals in today's this thing, and decarbonization. They all go hand in hand. All right. So now let's quickly touch about energy efficient products and solutions. Key influencers and decision makers. In this call, I am sure at least one of you represent, or many of you represent under one of the categories. There is a builder and developer who is definitely worried about the capex. He's worried about his cash flows. He's also worried about his end user preference. And very few builder and developers we come across who talks about OpEx as a language. Architect, who's actually the director of the show, he is certainly worried about the space optimization. He has to do best in the given space. He has to, by the way, also look at aesthetics, because that's where his, design philosophy lies. Structural requirement, and of course, he also keep it in mind that, what are the future expansion to be looked into, how the space provision, planning, everything definitely falls under architect, but many more responsibility. I've just highlighted a couple of them there. Cost consultant. Fortunately or unfortunately, they have become part of the entire system today. It's good to have the cost consultant who can give the visibility of all these ideas coming together. What does it mean? But very rarely, the cost consultant touch base with all the experts in the industry and provide that kind of a budget estimate to the end user so that he can think of sustainable solutions. Okay. Well, they are doing a good job in terms of providing the great benchmarking, then rate comparisons and things like that. But my request to this community is that in case if they start looking at sustainable solutions and then start popping up reports around that, maybe our customers also get interested from the CapEx and OpEx angle as well. Then the service consultants. I'm not going to talk about any other service consultant today, mostly about service consultants which are pertaining to HVAC designs. They talk about design aspects, the configuration possibilities, technologies and efficiencies. They definitely do justice to their job. And only thing right now they are also harping around is something which is a proven design and concepts. There are a lot of concepts which are probably new to India, but maybe proven elsewhere. The ask here is that why don't we look at the case studies which is proven in the other country and adopt that design? Be bold in this. Then, of course, the green building consultant. We see that there is a lot of disconnect between a green building consultant's wish list versus the practical feasibility at site. Okay, these guys are very much okay as long as they are trying to get their customers a platinum rated buildings or something like that. But we need to strike that balance. Then the MEP contractor and the key turnkey contractors, we all know that everybody picks up a job at certain price. Meeting the tender compliance is their goal and be price competitive. Honestly speaking, very few MEP contractors go after, look, this is my building. I need to turn this building into one of a sustainably most, benchmark building. Very few. I'm not saying that nobody does it, but very few we see. And then the facility management. I don't have to talk about this. Well, we will move on. But how does they influence and what stage they do influence? There are multiple stages in a project, right? So there is a concept stage, there's a design stage, there's an options evaluation stage, then the technical evaluation stage, tendering stage, procurement stage, and then project execution stage. Unfortunately, we as HVAC team gets the tender and then start working around that. By then, most of the design related decisions are already taken. Even if I want to add value to that project, I have got very limited choice because probably the plant room is already decided, structure is already come up. There's very little which I can do. So the ask here is that to anybody, if there is an architect in this call, please do involve us, not only HVAC as a service provider, all the service provider, do a workshop, take their ideas, just incorporate those ideas into your concept development. And when during the design stage, whatever suits your design, you can always keep them. And then you can evaluate the option and go on. Right now, this is being done only at the HVAC consultants end. I'm sure HVAC consultants are feeding the builder and developer and the architects. That's how the cycle works. But if at all we have to talk about sustainable solutions, I think there's a little bit more beyond what we are currently doing. I think that's the ask from the industry currently. Then HVAC market scenario. We all know that whenever we want to talk about any product or a solutions, everybody will need definitely these things, which is like, the product or a solution has to be reliable. It has to be pretty much flexible, user friendly, and operator friendly, something which is given. Has to be futuristic, smart, long lasting, efficient, economical. It should comply to industry norms, and it should also elevate industry benchmark. Well, these are all some of the expectation. They have to cater to this expectation also by adhering to industry guidelines. We all know entire HVAC market follows ASHRAE and ISHRAE guidelines for majority of the things. I would say entire industry is governed by that. Then when it comes to the product, we are governed by the certifications, AHR certified or Eurovent certified, or many other certification. When it comes to electrical, we talk about UL. If it is harmonics and VFDs, we talk about IEEEs. All these things guard our industry. With this, what is that we can do? So there is a design stage, implementation stage, and operation stage. And if the goal has to be net zero, so there are very high level key pointers. It starts from heating and cooling load calculations. And we add certain diversity factor, arrive at plant capacity and the configuration kind of thing, then go to the feasibility studies, then we do the technical evaluation, and then refrigerant choice. I'll take a couple of minutes on this as well. And then you talk about budget. So, well, when it comes to HVAC, we cannot live without cooling load components. So we all know in this learned audience definitely know that what all contributes to this. There is definitely the glazing parameters and the wall parameters, window to wall ratios. They matter to a greater degree when it comes to the cooling load component. The kind of lighting which we use, these numbers which I have given here are just for reference. Today we have reached a very good scale and efficiency in terms of each of these parameters, just for information. Computer loads, today we are talking about just like 65 to 50, 65 to 70 watts or something like that per computer. Occupancies, right? And the fresh air requirements. Over and above that, in case if you are targeting some green building, they say that you use this ASHRAE guideline plus 30% is also required. So what all this cooling load is comprising of? Mainly three parameters. One is external, then internal, and the system related challenges. External is anything which is beyond and your control. It can be the weather conditions which affects your building, can be dry bulb, wet bulb, humidities and things like that. It can be your windows and the glazing types, right? The shading coefactor, the transmission gains, infiltrations, all this can be external. When it comes to internals, it is mainly to do with people who are occupied in that building, the kind of activity that people do in that building, right? If you are sitting comfortably in an office, probably your sensible load may be around 245, total is around 440. But if you're dancing, obviously, it goes to 850. We know that, we add to both sensible as well as latents. Then the kind of lighting we are using, the plug loads, right? Unfortunately, the manual calculations only take into these things, but there is something to do with system efficiency losses as well. There's a lot of heat which comes from all these system related challenges, which is with ventilation, fan heat gains and things like that. So how do you calculate that? There's a big challenge with the industry. Today also, I can claim that nearly 70% of our community still uses manual Excel-based heat load calculations, right? Very few, maybe 30% are using the software-based. In that also, very few selected are using ISHRAE or ASHRAE approved selection softwares. So ask is, please migrate to something which is software based. Why? Because the Excel based has its own challenges. You cannot be dynamic with that. If one particular change happens in the design, you have to redo everything. Secondly, there's a lot of scope for human error. Thirdly, you are dealing with instant values, not the dynamic values. You are taking one particular published history or ASHRAE data or for a weather data, and you're trying to come out with your designs. It is not calculating for your heat mass and things like that. There are many ways of doing it. Okay. Today, we stand at a stage where either ASHRAE transfer function methodology or heat balance methodologies are used in the calculations of heat loads. Well, another enemy to us, to the industry for that matter, is safety factors. But why do we take safety factors? First and foremost, key parameter for that is, there's a lot of time. Data is not available with the, designer. He's been given one drawing, but not with much of a data. Wall material inputs, what kind of a wall he's designing, what is the thickness of the wall, properties of that, glass, insulation, the ventilation requirements for that matter, lighting and equipment load. He doesn't even know who is a tenant and how will he give you occupancy data. He's been told that you assume and work out. Weather profiles. Are we really working on 8760 weathers? Are we complying to the code requirement, ASHRAE 90.1 requirement, ASHRAE 62.5 requirement? All these requirements, are we really looking into that? Then are we calculating the overall system losses? So these are all the questions which are there in the mind of an engineer, an HVAC engineer who is designing it. Hence, what he does is he calculates the loads. He adds maybe about 5% sensible load as a safety factor. And then a certain safety factor added for the air terminal. And then finally, when he puts smaller safety factors, it goes as high as 28%. I've just taken a small example here. Over and above that, think of a situation where you have calculated a space and that space has given you a tonnage as, let's say, 1.2 tons. Now, will you get a 1.2 tonner in the market? If yes, well and good. If not, what as a designer you propose? You go to the next higher size which is available. Let's say 1.5. You have already given 0.3 tons extra over and above the requirement, right? That's how safety factor comes into play. Now, so how do we address this? There's something known as hourly analysis program, which is a software tool, which can help you in calculating the peak cooling and heating loads. Of course, India, we don't deal with heating loads much, but mostly the cooling loads, barring few, very few, locations. Then it helps you in system and equipment sizing. It can help you in energy modeling. Lead documentation. I mean, lead will go by the reports which are the outcome of a regular software which is approved by them and the code compliances, right? So this is mostly applicable for buildings, high-rise buildings and all that. We are also trying to see that if it can be applicable for other industries which are like on the rise currently, like a data centers and all that, but we'll address that in a separate session. So how does it help you? It can help you in energy analysis. Sorry?
Interrupt your flow another 5-6 minutes for your presentation, please.
Sure. Yeah. So it can help in energy analysis. It can help in airside systems, plants, multiple things. There are a couple of things, many architects would be using some other, tools. It is okay to use, but only submission here is that when you are designing a system where you want the outcome has to be proven one, please do use which are dedicated for that particular service. For example, you may probably look at HAP as a solution when you look at HVAC. So multiple capabilities, I just touched upon this. There are energy analysis possibilities. You can compare a lot of scenarios. You can compare various types of equipment. Maybe you can compare a VRF system versus a chilled water. You can compare multiple building orientations, right? 90 degree, 180 degree, 270 degrees and things like that. And it can help you with a lot of other reports, plant equipments, energy modeling. Think of what you can do with a building. You can probably do with this selection softwares. I have just put one small case study. We have taken a small office space where 4,700 square feet, very small. Like that, there are 10 offices and it's a 10-story building. In a case one, when you think of a weather, I have taken 0.4% and 1% scenario. With 0.4, I was getting a load of around 18 tons. And with 1% weather consideration, I was getting a load of around 15. How much that translated to? It translated into, let's say, 1,800 for one case and 1,550 for another case. What does that mean? It simply means that when you put all the factors, in this table, I was able to save close to about 281 tons of CO2 equivalent. That's the power of using a software-based, solutions. Well, what happens with oversized plant? I need not have to tell very high-level pointers. Increased capex, increased opex. You also will have to increase your electrical setups, then water requirement, and also the footprints. These are some of the capabilities of HAP. We can probably skip this. You can do wonders with this. A lot of building wizards are there, equipment wizards are there. You can do multiple iterations with this and it can throw the result in just like that flash. It also comes with the integration with Energy Plus, right? That's a lighting and HVAC can go hand in hand. Okay. And then most importantly about scheduling. When you do this scheduling pakka or properly, you don't have to consider the diversity factor because you're already accounted for all possible room occupancies and you have plugged that loads properly. So it can give you multiple reports like weather reports, system design reports, energy reports. And by the way, by doing all these things, you can for sure reduce the demand. When we say reduce the demand, our intent is not to reduce the plant room and suffer the clients. It is to right size the building by using the scientifically proven tools and do that. And once we do that, obviously you have multiple ways of optimizing your product. How to choose a product, I don't have to teach you this. You know that there are lots of options available with you based on your, weather conditions, based on your project goals. You can think of chiller classification, whatever the way you think of, lots of options available. Okay, so today's class we have focused mostly on the heat load optimization and the cooling load optimization. Let me give you one quick thing here. If we reduce the total cooling demand, we can also reduce the refrigerant requirement in that. And by the way, any direct emission is coming under your scope 1. You are contributing there as well. There are multiple refrigerant classifications are there. Some are already phased out based on GWP and ODP number. I want you to look at the possibilities by using the futuristic refrigerant. But you need to also strike the balance between the TWAI, which means my previous slides, this one. Am I focused around only direct emissions or I have to really look at indirect emissions as well? TEWI is a word for total environmental, impact. Please look into that as well and you can, come out with your solutions. Now, any building for that matter, no matter how you design, will always have some variance in terms of your, operating pattern with installed capacity. Hence, we would like to just leave with you a couple of thoughts that there are technologies available with company like Carrier, which can help you in optimizing your plant also, no matter how the plant is designed, but also is designed for taking care of the life cycle of the building at any part load. That's what, we can offer. And today's chillers are coming up with environmental product declaration, which is EPDs. Over and above your AHRIs and Eurovents and BE star labeling, EPD is playing a vital role, which is also catching up with the trend. I think with that, I will probably conclude here because in the interest of time, a lot of plant manager and plant optimization strategies are there. I mean, this is an endless topic, right? We can offer multiple solutions from our side, like modernization solutions, upgradation, BMS, and many more. In a building, think of HVAC. You can think of Carrier, by the way. So that's it from my side. I think probably I'll take questions and then we can deliberate on that. Over to you, Ritubrit.
Thank you, Prashantji. Almost on time. Thanks for that. So with that, I will hand over to my colleague Ranaveer to take up a couple of questions. We'll try to club questions and for the benefit of the wider audience, take up the most key ones. And whatever we miss out, Prashantji, we will request you to look at the Q&A section. And if you feel, one or two of them can be answered, typed out directly by your side, you can do that.
Sure.
What to you, Ranaveer? 5 minutes. Thank you.
Thank you, Dutta. So, and thank you for the insightful presentation, Mr. Dixit. So we have received some insightful and pertinent questions from the attendees. The first one I am posing is, so first question is, refrigerant leakages from HVAC systems are a major contributor to GWP. So what role should AC manufacturers and refrigerant producers play under EPR for effective refrigerant management? The second part is, are there existing legal compliances or related frameworks governing this in India? That's
okay. Sure. So first and foremost, responsibility is making sure that we select any equipment which has the lowest leakage rate, right? That's where it starts. There are a lot of systems available today, which claims that less than 1% of its overall charge annually is the leakage rate. We need to definitely ensure that, we select, equipment around that. Secondly, well, there is no guideline per se from the government legally, but there are guidelines governing the industry, especially when we use refrigerants, which does not fall under A1 safety classification. When we say A1 safety classification, a refrigerant which is very less in toxic and non-flammable. So there are guidelines. If at all you are using anything over and above like B1 classification, you are expected to use refrigerant monitoring systems and things like that. There are a lot of solutions available around that as well. Yeah.
Next is what is the best design kW per TR for centralized chiller plant, including high side and low side? Any increase?
Oh, okay. So I mean, I would say that, given a choice, we should go with natural ventilation, even being a, a HVAC person. But yes, I mean, today we are talking somewhere in the range of around 0.45 to 0.5 IKW per TR as an annualized plant room efficiencies are considered to be the best, given the limitation that the equipment efficiencies, given the limitation that the operational excellence which our folks has, and the controls which we're going to employ. So anything in the range of 0.4 to 0.45 is something which is excellent, I would say. But yes, there are possibilities to do the designs with that kind of ambitious, IKW per TRs.
Absolutely. Okay. So I think we can take one more question. If one is interested in cooling as a service and deep retrofit, how can we go ahead on these for the cooling as a service and deep retrofit things?
Okay, so cooling as a service is something which is evolving in India. It is a pretty much proven, solution elsewhere, like in Gulf and rest of the countries. We as Carrier also are into this space. We can definitely connect one-on-one for a detailed discussion. We do have solutions available around that. There are different models available in CAS model, we call it. Some people call it EAAS, Energy as Service. I mean, this is an evolving field, but yes, we are also evolving along with the industry on this. We can probably take offline this particular. Whoever is asked this question can get in touch with me. You can share my contact details with them.
Yeah. Thank you for very well articulated and clear answers. Perhaps for the sake of time, we can move to
Prashantji, one question, the tool that you showed, so how do people, the audience, get access to it? What is the model of subscription, cost, and so on? If you could elaborate a little on that.
Okay, so currently we are working with two different versions of it. One version is known as a 2D version, wherein which is considered to be based on our historical users. And there's a latest version which has come with a 3D version, which has the capability to even incorporate BIM modeling and all that. So, I mean, I don't know if it's the right forum to discuss on price and things like that. Maybe I think you can, because it depends on number of users, the versions they take, and multiple options around that. You can definitely share my contact coordinates, and we can do that.
Do look at the chat box when the other speaker is presenting. Probably you can answer a few. There is a lot of interest in what you have presented, which is a
Sure.
good thing. But for the sake of time, we are not able to take up all of them. We have collated and taken a few of them. And we will also, collate these questions, or you may mail. I am addressing the audience to info@aeee.in. We will connect you with Mr. Dikshit, collating all the queries that we have got, and probably you can take forward the discussion. That's our role as a webinar organizer and a facilitator in the energy efficiency ecosystem. So with that, once again, thank you, Prashantji, thank you, Ranavi, for facilitating the Q&A. With that, I would request my next presenter, Mr. Bose from Triveni Turbines, to please unmute yourself, share your screen, and begin your presentation. As I said to the earlier speaker, sir, you will have 25 minutes to present, and at the 30 minutes to 25 minutes to present, and at the 20th minute, I'll bring you just as a reminder. Thank you. Over to you, Mr. Bose.
Thanks a ton, Ritabrata. So, and thanks a lot to Pramodji for setting up the context, and also thanks for the wonderful session by Prashantji and taking this forward, whatever the context which has been set by Pramodji. So let me share my presentation. Give me a second. Let me know if it is visible to all of you. Am I audible? Hello?
Yes, sir, you are audible. Please go ahead.
Yes, yes, you are.
My slide is visible to everyone?
Please go to full screen mode, Mr. Bose. Please go to full screen.
Yeah, sure.
Yeah, now it's fine. Go ahead.
Okay, a little brief about Triveni because the topic on which we are discussing and the industry is HVAC. And Triveni, in a way, we can say it's a latest entrant in this field. However, we are predominantly a turbine manufacturing company. We have two verticals. One is Triveni Engineering and Industries. It has got again sub two verticals. One is the cogen business, where we are manufacturing sugar as well as alcohol, and we are also generating power, which we are basically selling back to the grid. And then we are also having engineering businesses under Triveni Engineering, where we are making some components for power transmission. We are providing solution for wastewater and also for defense. I'm coming from Triveni turbine side. So here we have some offices obviously in India, as well as we are based in abroad also, like in Dubai, Europe, South Africa, Thailand, as well as in United States of America. We have our offices. Moving on. So far, we have delivered over 6,000 steam turbines globally and set up 16 gigawatt of power generation facility or capacity. This installation has happened in over 80 countries, and 20 plus different industries have been served. Incidentally, wherever we have supplied our turbines, nearly 80 to 85% of those businesses, they come from the thermal renewable fuels. And we are having more than 30% market in sub 30 megawatt capacity of steam turbine. Moving on, this is our global footprints in 80 countries. We have our headquarter based in Bangalore and subsidiaries, as you can see. Moving on, I'm talking about the new technology. Under this new technology, we have different offerings. It starts not in sequential way in any way, but it is like ORC turbines. We have air expanders, supercritical CO2 turbines, subcritical CO2 turbines, natural refrigerant based heat pumps and chiller, and then mechanical vapor recompression. This is all part of our solution for energy transition. Moving on, I'm coming to heat pump, which is the topic for the day today. And predominantly today, I'm going to talk about heat pumps based on natural refrigerant. But before we go into heat pump, basically we need to know, and many of you probably are already aware of, that where we are on the refrigerant and what is the international policies say. So we, being one of the countries which has also agreed not just on Montreal Protocol, also as a follow-up on the Kigali Agreement. So we are following up accordingly what has been decided when we have to phase down what all things. Coming back here on the refrigerants. So HCFC, as we all know, is anyway going to get phased out. Already it has been phased out to a great extent, but I believe formally by 2030, it is going to be totally phased out. Even HFC also, the phase down has already started. For us, the target is 85% reduction by 2047. I believe we are probably well ahead of that curve as at present. And HFOs also we have, which is again lower GWP and lower ODP, refrigerants. Then we have natural refrigerants. As you can see, natural refrigerants, we have propane, isobutane, ammonia, CO2. So we are going to talk about all this, or predominantly about CO2 refrigerant based heat pump today. Moving on. So I'll not go into the GWP and ODP, which is anyway visible to you. We are talking about some certain benefits which we have whenever we use the low GWP and the ODP products, which is, by the way, low GWP, I mean global warming potential. ODP is ozone depletion potential. So the natural refrigerants are very climate friendly, quite energy efficient. Even the operating cost also is low, and it is widely available and relatively cheaper. However, we face some challenges also. When we talk about challenges, there is inflammability is one of the challenges, with a few examples like propane, isobutane. Then toxicity is another challenge. If we are going to use ammonia, we are using ammonia, but toxicity is the issue. And when we talk about CO2 system, it is quite high pressure system. So that is another cause of concern or challenge. Moving on. So this is the picture which you see. It is one of the demo heat pump which we have designed, assembled, and which is under testing at present. We have a technical collaboration with Indian Institute of Science in Bangalore here, and also we have a technical tie-up with NTNU University, which is Norwegian Technical University based in Norway. So we have a tie-up with them also. And outcome of that discussion which we initiated, or which the thought process which we were having towards bringing low GWP and low ODP products, this is one of the outcome which has come. So before moving a little bit on the heat pump, I'm assuming majority of you know, this is through which we can get simultaneously heating and cooling solution. This provides that basically. Now we talk about CO2 heat pump. Basically, CO2 as a fluid has a unique property. Its critical point is 31 degrees Celsius and 73.8 bar. What is mean is that beyond this, it is in supercritical stage. Below this, it is in subcritical stage. And if we are using both the phases of this fluid, basically it is moving between supercritical to subcritical, and because of which we are, the outcome which we are getting through heat pump is the heating and cooling. And that's where we call it transcritical CO2 heat pump, or in short, TCO2 heat pump. The one which is right now in front of you, basically it produces, we are taking ambient water, let's say at 30 degrees Celsius, and it gives the hot water at 90 degrees Celsius. There is in between, we have put a heat recovery unit also, where because of that, it also gives us a 65 degrees Celsius water too. I'm talking about this particular unit. And this combined COP is 5.9. So this gives 110 kilowatt of heating and 77 kilowatt or 22 TR of cooling. Right now, the system is under testing here. Moving on, just want to explain how does it functions. Basically, this is self-explanatory still. So as I was mentioning, from the customer point of view, he needs a heating and cooling solution. And heating here, we are talking about 90 degree or above. The one unit which we have assembled, it can give the heating up to 120 degrees Celsius. In fact, during our testing, we found it has given us 122 degrees Celsius, and the cooling at 7 degrees Celsius, which I believe at present, the HFC based system cannot provide that because of the limitation due to the refrigerant which is being used. Now coming back to how it functions basically. So as I was saying, so there is a heating and cooling requirement to any of the client, and based on the data which they provide, like what is the ambient temperature water is available, what is their expected heating water which they need, and the cooling water which they need, or the chilled water which they need, and the flow rate, etc. So based on that, obviously we do the selection of the compressor, and this process is quite, from that point of view, easy to understand. Obviously, this is a closed loop system. When we talk about this CO2 or TCO2 heat pump, it's a closed loop system. So here we have the compressor, I'm not sure whether my cursor is shown to you. Is it visible? Okay, I'm assuming it is visible.
Yes.
So, okay. So the compressor basically, which we select based on the criteria which has been given to us. So after the compressor selection, that compressor basically it compresses the CO2 which passes through the gas cooler. And here the temperature is quite high. I will talk about a specific example later, but here just to make you understand. So this high temperature CO2 passes through the gas cooler where we get the ambient temperature water, and it gives it back at 90 degrees Celsius or more. Post which it passes through the internal heat exchanger where obviously the pressure remains same. However, the temperature comes down a little bit, and then we pass it through a high pressure valve expander, which we can say, and it from here it goes to something which we call intermediate pressure receiver or IP receiver. Here the CO2 comes in two phases, in liquid as well as in gaseous form. So the gaseous form, which we again pass it through a flash gas valve, and we put it back to IHX, from where it goes back to the compressor again. Here, when we talk about this liquid CO2, it comes out and it passes through a expansion valve. And here what happens, both the pressure as well as the temperature comes down. And temperature normally is around 3 to 4 degrees Celsius. So the water which we are getting, let's say from chiller or from anywhere else, at 12 degrees Celsius, it gives it back at 7 degrees Celsius. And the CO2 again goes back from here to the compressor. So this is how it works. Important thing here is, as compared to the other heating or the heat pumps, we are getting a relatively huge COP of 5.9. So which is something very, very, I would say energy efficient, and it is one of the green product, as you all know. So this is what the benefit of using the transcritical CO2 heat pump. Moving on, this is one CO2 based, same principle, one chiller which we have assembled for Indian Navy. It has been installed at INS Shivaji, Lonavala. It has run more than 3,000 hours, and it has been inaugurated formally by Chief of Naval Staff in January 24. Moving on, I just want to give an example here of savings through transcritical CO2 heat pump. Let's assume you have an existing chiller of 1000 TR capacity, which is giving a process cooling temperature 7 degrees Celsius. It is giving for process cooling, and obviously the return temperature is 12 degrees Celsius. So this is how it is working. So we would like to, what we want to do to decrease the pressure or the loading on this particular chiller, we will take a tapping from this 12 degrees Celsius line and we will send it to the heat pump. Okay. Now this heat pump, which we are talking about, a transcritical CO2 heat pump, it will take that at 12 degrees Celsius and it can give back at 7 degrees Celsius. In this process, and 7 degrees Celsius again goes back to the 12 degrees Celsius line, not at 7 degrees Celsius line. It will go back to 12 degrees Celsius line. Here, when we are talking about this heat pump, what basically it is doing, it is also providing the heating solution. So the ambient water, which is, let's say we are getting at 30 degrees Celsius, it is providing the hot water at 90 degrees Celsius. In this entire thing, as you can see, the power which is being consumed by the compressor is 32 kilowatt. And in other turn, we are getting a heating of 110 kilowatt and cooling of 77 kilowatt. Now, if we do the calculation going further, this is also providing a steam saving of almost 185 kg per hour. And here, if you see, because this is a 100 TR unit which is already there, it is getting additional 20 TR of further cooling. So there is a 22% capacity, in another way you can say capacity reduction because of the heat pump. Moving on, if you do the calculation of COP, obviously it comes out to be 5.8, and if we do the calculation of energy 7, it comes out to be 150 lakh rupees per annum, where our assumption is that steam cost is at 5.2 rupees per kg, electricity cost is at 8 rupees per kilowatt. I will show you the detailed calculation going forward for one more similar exercise like that. But this is what I want to show here, that the advantage of using the natural heat pump is immense. Moving on, here the benefits of CO2 heat pumps. One is obviously it provides the heating and cooling simultaneously. It is almost as good as like a IC engine. Like in car, you just sit there, you start the car and it just starts, the engine starts. It is like that. I mean, where, as compared to HFC, which it takes maybe anything from 45 minutes to 1.5 hour, depending upon the capacity of the heat pump, where it takes more time, this provides almost simultaneously heating and cooling solution. This is another advantage, is it's quite compact, very compact in nature. And this is, I'll go forward and I'll talk further about one of the application. Just keep this thing in mind when we will talk about the advantage of its compact size. It can give a maximum temperature up to 120 degrees Celsius, which we could able to achieve here. And because of higher efficiency or COP, the ROI, return on investment, is relatively shorter as compared to existing heat pumps. This is quite safe. And needless to say, this is a low CO2 footprint product. Moving on, the industry-wise application, if we see where all it can be used, it can be used for several industries, as you can see, right from paper industry to marine to dairy and food industry, sugar industry, chemical and pharma industry. So all these industries it can be used. Moving on, so I was talking about that one CO2 chiller which we have provided to Navy, and they are quite happy. They have used it for more than 3,000 hours. The plan which is there, and it is not just for Navy, it is for any ships which is using the existing heat pumps, which is providing the chilling as well as maybe some certain part of heating. There, those things can be replaced by this natural refrigerant based heat pump. Why? Because it is quite compact in size, and it is a green product, environment friendly, and efficiency is also quite high. So this is one of the application I'm just talking about here. Now, if we talk about other application, so most of the places where steam is being used, obviously there is a boiler. So if we have to reduce the fossil fuel which is being used, for boiler, that we can reduce to a great extent by adding this heat pump. Same philosophy once again, as you can see, 30 degrees Celsius is in and 90 degrees Celsius is going out. Compressor is there, I mean, which is obviously pumping it at let's say, if we talk about very specific to this particular case, here we have a compressor which is giving at 125 degrees Celsius, the CO2 temperature at 115 bar. And moving on, once the water comes in at 30 degrees Celsius, it goes out at 90 degrees Celsius. And then this CO2 at 115 bar and 32 degrees Celsius, it goes to internal heat exchanger here, and where again the temperature comes down to 27 degrees Celsius before it goes through the HP valve, which is high pressure valve. Once it passes through that, obviously it gets expanded. So the pressure also gets reduced to 50 bar and temperature to 12 degrees Celsius when it moves to the intermediate pressure receiver here. Here the phase change happen. Some part of it is in gaseous form, CO2, and some part is in liquid form. And as I was mentioning, the gaseous at 12 degrees Celsius, it again goes through, we flash it through a valve to this line, which is going to internal heat exchanger. And from here, it goes back to compressor. It is all in gaseous form. Now this liquid one, it comes down at 50 bar pressure, and it goes through the expansion valve here, and here the pressure after that expansion, it becomes 38 bar and 3 degrees Celsius temperature, which is the chilled water which is coming from the return temperature of the chilled water, which is coming at 12 degrees Celsius. Now this can make it 7 degrees Celsius. We can provide at 7 degrees Celsius. So obviously it reduces the load on the existing chiller, as I was mentioning earlier. And this CO2, which was here after the expansion valve, through this evaporator, it goes back to, through IHX, internal heat exchanger, goes back to compressor. So this is how the loop gets completed. It is a closed loop application. And so here, very important thing is the system will be efficient to, as what we are mentioning here, like for example, if you calculate, it comes out to be 5.2. And this will continue to be efficient that way, provided there is no leakage. And so leakage of CO2 is something which we as a manufacturer have to be assured of, that there is no leakage. Moving on. So this is the calculation I was talking about. If you see here, like in previous example, what I was mentioning, here is a savings of, due to the TCO2 heat pump in this particular application, around 137 lakh rupees per annum. And all these things are possible because of higher COP of, which is as compared to the other refrigerant we are talking about. So this is something which makes a prominent thing, like why we should be using TCO2 based heat pump. However, one more thing which I want to add here, TCO2 heat pump makes sense only when you go to those applications where the delta temperature is higher. Like you want to heat it from 25, 27 degrees Celsius to 90 degree or above. And you want to have the cooling solution also. So that is, these are the places it makes sense. Moving on.
Sorry to interrupt. 5 minutes more.
Sure. Moving on. So there could be a question, why natural refrigerants, why not HFOs, even though HFOs or what we say hydrofluoroolefins are also low GWP and low ODP refrigerants. But as per the latest study, it gives the chance of PFAS. It increases the PFAS. It's a kind of pollutant which is generally, it goes and get part of the soil and the environment, which can contaminate the drinking water as well as the food source, and it can cause it could be one of the reasons for cancer. So the latest studies are basically discouraging use of HFO, and that's where the some other natural refrigerants are also plays a critical role. When I was talking about CO2 based heat pump, here I was mentioning that delta temperature is supposed to be more, but many places where the delta temperature is not high, let's say the heating solution is required at 115 degrees Celsius, but the return is around 105 degrees Celsius or so, and that is the time when CO2 is not advantageous to be used. So that place we can use isobutane or butane refrigerant. Similarly, when we talk about some chilling thing, there also, if the delta T is not high, we can think of using propane. Moving on, actually this is it. So that's all from my side.
Thank you, Mr. Bose. Almost bang on time. Same process as earlier. I would hand over to my colleague Ranavi to facilitate the Q&A for the next 5 minutes. Over to you, Ranavi.
Thank you. So the first question is, what is the
Mr. Bose, you can stop sharing your screen if that's all right.
Yeah.
Go ahead.
yeah, okay. So what is the heat pump suitability in space heating in Indian Himalayan region? And what are the other sectors in industry where heat pump can be installed? And how can heat pump be beneficial for data centers? I have combined 3 questions into one. So
Yeah, I'll go one first, and then you can repeat this last 2 questions. So your question was for Himalayan region, right? So Himalayan region, this could be one of the very good heat pump which can be used. As we all know that in Himalayan region the temperature goes quite low. So for our soldiers and many other people, this could be something really good where we can use a natural refrigerant based heat pump. Again, it depends on the application to application, where we can pick and choose either a CO2 system or we can choose a isobutane or butane system. But it is definitely, it can help a lot.
okay. So second
What
one,
was the other 2 questions?
yeah. So what are the sectors in industry where heat pump can be? I mean, what are the other sectors in industry along with the data center where heat pump can be installed and benefit?
See, as of yet, based on what we have studied, some of the sectors I have already mentioned earlier. But if you talk about any process industry, be it pharmaceutical, be it textile industry, okay, where they are using a lot of heat for some secondary processes, or they also want cooling as a byproduct. So there it can be used. It can also be used in commercial places, like let's talk about a new big hotel is coming up, and they want hot water for bathing purpose as well as for their kitchen, and cooling they want to do the air conditioning for all the rooms, so it can be used there. Same is the case for commercial buildings like big malls, etc., where the hot water can be used from the kitchen point of view or any other processes which is there, and cooling can be used uh, for the air conditioning purpose.
So the second question is, heat pump is running on simultaneous heating and cooling. So what happens if you do not have a cooling water source? And the attendee had asked how much carbon can be reduced through this heat pump. So I mean, he meant by this heat pump means the case study that you have presented. So is there any calculation of the carbon reduction also using those heat pumps?
See, this is first thing is we know that from the GWP and ODP point of view, which is a proven fact from the natural refrigerant point of view, that it is quite low. So and when it comes to emission, there is no emissions at all, because it's a closed loop cycle which we are following. So there is no emissions at all.
Okay. The third follow-up question is basically, I think you all partly have already addressed. Kindly suggest transcritical CO2 heat pump can be used in closed loop system like 90-80 degrees C hot water application or once through the system.
As I was mentioning, that transcritical CO2 system can be used where the delta temperature is high. That means if you are going for a ambient temperature to a higher temperature or something like that, that is where it makes sense. That's where your COP will be on a higher side. Otherwise, even if you go for that, either you have to dump lot of cooling or heating, to the cooling tower, etc. It will not make sense. But if you talk about the delta temperature where it is less, let's say, as I was giving an example of isobutane, where the delta temperature is less, but you need heating as a primary requirement. So isobutane can be considered for that particular use.
One question we'll take. The next one is, how do the capex cost in case of natural refrigerants compare with that for equipment based on fluorinated refrigerants?
A very good question, first of all, whosoever has asked. So here, refrigerant cost is not much. That is not an issue. Our issue is because it's a very new technology and many of the ecosystem is not yet developed. At least in our country, the ecosystem is not there. So whatever you have seen in that picture of the heat pump, which I was sharing earlier, so most of the components as of yet is imported, whether we talk about compressors, because it's a high pressure compressor. The pressure itself goes up to as high as 115 bar or so, right? So that is one issue which we are facing. Like we don't have that infrastructure where this compressors are available readily in India, which are being manufactured and which is not the case. So we are importing this. We are also importing the heat exchangers. So all the heat exchangers are also not available as of yet here in India, which is being manufactured in India. It is not available. Same is the case for majority of the components for walls and many other components, which we are also have to, so far we are importing. So coming back to the capex, at present capex is high. But when you talk about the life of this heat pumps, which I was talking about, it is 25 years, 25 to 30 years, right? So when you see the ROI, and most of the cases when we are doing the ROI, because of the high efficiency level, whenever we are doing the return on investment calculation, it is coming within 3 years. In that way, I would say, even though the ecosystem is not here, imagine if the ecosystem is available here, maybe the return on investment will come close to 1 year or maybe less than 1 year. And considering the life of this heat pumps, 25 years or so, it is like a win-win situation for any customer.
Okay, so last question, Mr. Bose. What are the supply chain related constraints for the CO2 based heat pumps in India? Are there any challenges, for instance, in supply for instance, we talked about Indian Himalayan region and or any part of the country. So that is one thing. And what are the potential? What kind of potential do you see for the heat pump systems applicability for the commercial and residential heating and cooling application? Because you have demonstrated some cases where heating and cooling both can be supplied simultaneously. So what is the potential? What potential do you see for the commercial sector, commercial and residential building sector, as well as what are the supply chain constraints currently?
Okay, I think supply chain constraint I've already mentioned, because the ecosystem is not yet developed. So not that we can get from supply chain point of view, we can get the required parts and equipments from abroad. That is not a problem. But the lead time, by the time we get it over here, it's almost 6 months a time. And the cost is also on a higher side. So if we have to assemble for any customer, which we are trying to prepone, so it goes, at present, it is a challenge which we are facing until unless the ecosystem develops. So this is one challenge which we are facing. And from that point of view, you can say anything between, depending upon the capacity, if we have to deliver it to anyone, it is close to 8 months to, you can say anything between 11 to 12 months. So this is one of the big challenge which we are facing, because this industry, the present industry, HFC based industry, I mean, it is almost in 3 to 4 months, it is being delivered, right, from getting the purchase order. So this is one challenge which we are facing. But as I mentioned, this is a green product, environment friendly product, quite high efficient product. So if the companies can plan their capex upfront in a way, then whatever solution we will provide, as I mentioned, the ROI is on a lesser side as compared to the existing heat pumps or so. So then it will make sense for any of the industry, which whatever whosoever would like to have it.
Thank you, Ranavir. Thank you, Mr. Bose. So I won't hold you back. I understand you have another meeting in 3 minutes. So please, thank you very much for joining. But if it is possible, I will ask the same question to Prashantji as well. But for the paucity of time, I'll ask you first, Mr. Bose, if there is one takeaway that you have to give to the audience from Triveni's side, what would it be? You have heard both the presenters, you have seen the overall session. What would be that one thing that they should take away from Triveni and you?
I would just say we are on track with the government initiative of Viksit Bharat by 2047, and towards that, whatever we are moving towards net zero target. So here we are ready with the product, and believe it or not, it is the future, because eventually we all know that the existing HFC based heat pumps are going to be phased out. So this is the initial phase challenges, whatever we are facing, but we are very, very excited with the product, the highly efficient product, which is giving a temperature of up to 120 degrees Celsius. We are very, very excited about that. And I know, and I'm quite sure this is what going to come out sooner or later.
Excellent. Thank you, Mr. Bose. Have a good evening, and I won't hold you back anymore. But wonderful presentation.
Thank you.
A lot of interest on the stakeholders. Prashantji, from your side and from Carrier's side, what would be that one takeaway that you have to offer to all the attendees?
Well, I mean, I would like to take this opportunity first to thank AEEE for giving this wonderful opportunity, because this is a forum where think tank attends. I mean, that's what I've always believed, and this is my second or a third presentation with AEEE as a team. You always get the quality audience. Hence, my request to quality audience is that if at all you people feel that you have some urge to contribute towards sustainability, please upskill yourself. Be it in whatever the domain you are, please upskill yourself as a customer, as a consultant, as an advisor, influencer, whatever it can be, as a vendor. Please upskill in terms of the available technologies, available tools and tackles, available solutions around you. Discuss that with the learned colleagues or a group and things like that. And what can be more interactive session than this forum like this? Please do attend in good numbers in the upcoming sessions also. I've always enjoyed these sessions, and Mr. Bose also delivered a fantastic, insights about, carbon. And I would definitely like to connect with him separately on other knowledge sharing sessions. But yes, it's a wonderful initiative. I can only request the participants to stay tuned to AEEE. You have more to gain here. I can only, give that comment here, Rituparna.
Thank you, Prashantji. It's our privilege to have Triveni and Carrier as members. And not only Carrier and Triveni, we have 76 other members ranging from startups, consultancies, educational organizations, and from energy efficiency domain. So thank you very much. And Ranavir, you have been the bridge between the audience and the speakers. What is your one key takeaway from this session, if I may ask?
Yeah. So yeah, two things I have clubbed into one. One is that from the Prashantji's presentation, that integrating precision load, estimation early in the design phases helps curbing oversizing, reducing life cycle costs, and supports compliance with efficiency and compliance with codes and standards. So that is one important takeaway from the Mr. Dixit's presentation. And the second from Mr. Bose's presentation, natural refrigerants seem to be no longer experimental. They have come out of cells and demonstrated use cases in India, as Mr. Bose already presented. So, and they have shown very strong technical performance and financial viability across industries. So it's time to take off from the conventional refrigerant to natural refrigerants. Yeah, that's the whole thing I would summarize.
Thank you, Ranavir. I mean, if speakers have to leave, feel free. My last 1 minute is for the audience. So it is my pleasure once again to thank all of you for joining, dear participants. If you have any further queries, please send it across to info@aeee.in. We will facilitate your connection with the speakers. We will also send you a follow-up email. Unfortunately, we may not be able to share the slides, but the YouTube recording of this session, we will share the page where it is available, where it will be available in about a week or so. Please feel free to associate with AEEE if you feel there is an opportunity that you see of us working together. Please feel free to reach out to us through the same email ID. And there will be again our next webinar, episode 4 under IL0 series. And all of you will get an invite, and we hope to see you in equally great numbers and an equally energetic response. So thank you very much, everyone. Have a good evening. And with that, we bring today's session to a close.
Thanks a lot, AEEE team,
Thank
and to the
you.
audience also. Thank you very much.